Hello, good morning everyone. I am Dr. M.G. Srinivas, working as Associate Professor in the Department of Electronics and Communication Engineering, MIT Tandavpura. So today we will be discussing on the chapter Introduction to Transducers. Before getting into the topic, let us know the basic definition of a transducer. So a transducer is a device which converts a physical quantity into equivalent electrical output. So basically it is the conversion of a physical quantity to electrical output is called as a transducer. Okay. So transducer which it is the physical quantity that can be measured using a transducer or some of these. We can measure the force. So using a transducer, we can measure displacement using a transducer, we can measure pressure using a transducer, similarly temperature and humidity. So these are called the physical quantities. Using the transducer, we can measure, we can get the equivalent output of the force in terms of electrical output. Similarly, the displacement in terms of equivalent electrical output. So that is what is called as a transducer. Next we will go for the classification of transducers. So transducers are basically classified into two types. So based on active element and based on the excitation voltage. So based on the active element, so transistors are of three types. One is resistive transducer, second one is inductive transducer, and third one is the capacitive transducer. So when we come to the excitation voltage, there are two types. One is called as active transducer and second one is called as passive transducer. So let us understand what is meant by excitation voltage. Some transducers, so for its working, we should give external supply. So external supply in form of voltage. So those transducers are called as passive. Most of the transducers are passive transducers, because for their working they require external voltage. We call it as bias voltage. So we have to supply that bias voltage, so then only they can work. But there are some transducers which work without the excitation voltage. They are called as active transducers. So some of the transducers like thermocouples, piezoelectric devices, they are called as active transducers. So this is about the classification of transducer. So this is a resistive type of transducer. So the basic resistive type of transducer is called as a potentiometer transducer. So this potentiometer transducer is as shown in this figure. So now it consists of a resistive coil, so for which we are giving the supply of voltage of V, and it contains a movement coil, or we call it as the wiper, and there is a conducting strip. So the position of the wiper determines the output voltage. So here the movement of this wiper, it is going to determine the output voltage V of this resistive type transducer. So if you carefully look into this, it is a potentiometer. Here it is connected to positive and negative of the voltage, and this is called the wiper. If you keep on rotating this, the output voltage is proportional to the wiper, the position of the wiper. Okay. So this is a simple resistive type transducer. Type of resistive type of transducer, it is called as strain gauge type transducer. So a strain gauge is a resistive material in which whenever it is strained, so there is a change in the resistance. So now a strain gauge is used in the electrical circuit as Wheatstone bridge. So this is called as a Wheatstone bridge. So where it has got four elements, so connected as resistances. See here R1, so this is R2, R3 and R4. So there are four resistances. Okay. So here one of the arm of the Wheatstone bridge is connected by a strain gauge. We call it as the active strain gauge. So now whenever there is no strain, we call it as the balanced condition. Whenever there is no strain, so whenever the strain gauge is not strained, so it is called as the balanced condition. In that case, the output voltage V0 is 0. we call it as the strain gauge is in balanced condition. But whenever a strain gauge is strained, so the Wheatstone bridge gets unbalanced and we get the equivalent unbalanced output proportional to the strain. So this is what the working principle of a strain gauge. Now let us see the equation how we get whenever a strain gauge is being strained. So how the resistance changes. We all know that so the equation of a resistance is rho L by A. This is the basic equation of a resistance. So what is this rho? Rho is called as the specific resistance. It varies with respect to material and its unit is ohm meter. So where L is called the length of the resistance and A is called the area of the resistance material. If it is being taken as a wire, so we call it as area of the wire. Okay. So now how to calculate area? So area is given by pi d square by 4. I will substitute area as pi d square by 4. So therefore resistance is equal to rho L by pi d square by 4. So here whenever the resistance is strained, the length is increased, diameter is decreased. So this is obvious. So if I take a resistance material like this, so whenever it is being strained, the length increases whereas the diameter of the material it decreases. So that is what it is being written here. Length increases. So I have taken the increase in length as L plus delta L. And the new diameter, so since the diameter is decreasing, I am writing it as D minus delta D. So whenever it is strained, resistance obviously increases. As the length increases, resistance should increase, because if you see the equation here, R is directly proportional to L. So therefore the resistance should increase. So here I have written resistance R plus delta R. So this is what the changes that is going to happen. So whenever a resistive material used as a strain gauge is being strained. So let us see how to calculate the important factors so applicable to the strain gauge. So first is called as the gauge factor. So whenever we are using a strain gauge type of transducer, so these factors has to be calculated. First one is called as the gauge factor. How to calculate gauge factor? It is the ratio of the change in the resistance to the original resistance divided by change in the length divided by the original length. So this is called as the gauge factor of the strain gauge transducer. Then second one we are going to calculate is the Poisson's ratio. So it is defined as the change in the diameter to the original diameter divided by the change in the length to the original length. So these two are very important factors in a strain gauge. Now these two factors, gauge factor and Poisson's ratio, are related by the equation GF, gauge factor, is equal to 1 plus 2 times mu. So this is what the relationship between the gauge factor and the Poisson's ratio. Finally, so if you see this equation 2, so it is been given it as R is equal to rho L divided by pi d square by 4. Whenever this active strain gauge element is strained, R is going to change, L is going to change, and also D is also changing. So now I write the equation like this: R plus delta R, that is change in resistance, is equal to rho into L plus delta L divided by pi by 4 into D minus change in the resistance whole square. So this is what the equation of a resistance. So when we use as active strain gauge element in a Wheatstone bridge. So this is the one of the type of resistive type transducer. Okay, next type is inductive transducer. So inductive transducers are basically used to measure the displacement. So in this one we will see the first type. So variable reluctance transducer. So what is this variable reluctance transducer means? It is a type of transducer which uses the change in the reluctance reluctance of an air gap in a magnetic path to measure the displacement. So here, so this is the actual diagram of a reluctance transducer. As you can see here, this is a iron core which is called as the target piece, and this is a U-shaped, again a magnetic core, so which is been given the voltage, excited voltage here. So whenever the voltage is excited, excited voltage is given to this coil tries to move this iron target piece in the forward and the reverse direction. This is by the principle of electromagnetic induction. So whenever the magnetic core is being excited, so by the magnetic field, so it tries to move in forward or in the backward direction. So whenever it is moving, so there is a air gap is being formed. So that length I will take it as L. So this is the basic principle of the working of the variable reluctance transducer. So now if you see the equation of the reluctance magnetic type of transducer is, so R is called the reluctance, is given by L divided by mu naught into A. What is this L means? The length of the air gap. This length of the air gap depends on how much the excitation voltage we are giving. So if more voltage is given, so this air gap can be of maximum length. If the excitation voltage is reduced, the air gap is also of shorter length. So now here Rm is given by L divided by mu naught into A. So where mu naught is called the permeability of free space and A is the air gap cross sectional area. So this is what is called the cross sectional area of the transducer. So now using this one, so we are going to calculate what is known as the inductance. So how it is being calculated? So inductance is given by the number of turns that is wounded on the U-shaped coil here, that is N square divided by the reluctance. So N square divided by reluctance. I am going to substitute what is the value for Rm here. So we will get N square into mu naught A by L. As you can see here, mu naught is a constant. So A for a particular air gap, for a particular length of air gap, this area is also constant. So therefore I can say mu naught and A are constants, and only variable is this N. If I vary this N, so the air gap is going to vary. Whenever this air gap is going to vary, it varies the area also. So here the varying factor is the N. So coming here, so therefore we can say the inductance mainly depends on K, which is called as a constant, and divided by L. That is, inductance is inversely proportional to the length. Here length refers to the air gap length. So by varying the length, we can measure the inductance. Similarly, so the reverse is also like this. If I change the length of the air gap, inductance is also going to vary here. Okay. So now hence it is seen that coil inductance is inversely proportional to the air gap length. So this is what the working principle of a inductive type transducer. They are basically used to measure the displacement in terms of change in the inductance. Okay, this is the second type of inductive transducer. It is called as linear variable differential transducer, and shortly it is called as LVDT. So this LVDT is again used to measure the displacement. So it is constructed like this. It is a iron core on which 3 copper windings are wounded. One is called the primary winding. So it is connected to the source voltage, and the other 2 are called the secondary windings. Secondary winding 1 and secondary winding 2. And it has got the turns N1 and N2. The voltage across the secondary winding 1 is called as V1, and the voltage across the secondary winding 2 is called as V2, and it has got a adjustable iron core. So, it is a hollow metallic part. In this one, a core is moved up and down. So, whenever a core is moved here, the flux is induced and voltage across V1 and V2 can be measured. So, this is how the internally it looks like this. So, this is the single primary winding and these two are the secondary windings. So, and the primary is connected to a source Vi. Here the frequency of this voltage source is not 50 Hertz, it is a very high frequency of the order of 20 kilohertz. So, we use a high frequency source here to excite this primary winding, and whenever the primary winding is excited, the flux is introduced between the secondary windings, and the voltage across these secondary windings depends on the movement of core inside. Whenever the core is moved upwards, the voltage across the secondary winding 1 will be high, whereas the secondary voltage across this one will be low, because more flux is introduced across the primary and the secondary winding V1. Similarly, whenever the core is moved down, so the flux is introduced between primary winding and the secondary winding 2. Hence, the voltage across the secondary winding will be high compared to V1. So, this is as shown here in this waveform. So, this is the voltage across the secondary winding V1, it is called as V1, and this is the output voltage. As you can see here, the core is displaced up. Whenever this core is in the upward direction, so the secondary voltage V1, it will be high compared to the secondary voltage V2. So, now if you take the difference, so this will be V1 minus V2. So, the difference of the voltage gives the displacement. So, here V1 is starting from plus, whereas V2 is starting from minus. So, therefore, I have written V1 minus V2. So, the voltage is calculated between the difference of the secondary voltage V1 minus V2. So, this is for the first type of displacement whenever the core is displaced up. Similarly, so whenever the core is moved down, so the voltage across the secondary winding V1, it decreases, because now the core is very near to the secondary voltage V2. So, therefore, the voltage across the secondary winding V2, it increases. So, now as you can see here, V1 is starting from 0, whereas V2 is 180 degree out of phase. Now, if you calculate the displacement, again it is, if I say V1 minus V2, but since the voltage is very less here, we get the displacement as negative, whereas here the displacement as positive. So, that means that whenever the core is moved upwards, the displacement is positive. Whenever the core is moved downwards, the displacement is negative. We can measure both the positive and negative displacement using this LVDT. So, this is one of the type of inductive transducer. Let us see the working of the capacitive transducers. The equation for the capacitance between two plates separated by a distance d and having area A is given by this basic equation. So, capacitance is equal to epsilon r into epsilon naught into A divided by d. So, always the capacitance is directly proportional to the area of the plates, and so it is inversely proportional to the distance between the plates. This equation is called as capacitance of two parallel plates. Okay. So, here epsilon r represents the relative permittivity of the dielectric material, and epsilon naught is the permittivity of free space. It is equal to 8.84 into 10 to the power of minus 12 farad per meter, and A is the cross sectional area of the plates in meter square. So, now this is what the basic equation of a capacitor. So, these capacitor based transducers are basically used to measure the pressure or the displacement. So, we can measure pressure in terms of electrical output, or we can measure displacement in terms of electrical output. So, in this case, in this class, so we are going to study capacitive pressure transducer. So, how to measure pressure in terms of electrical output. So, this is a small arrangement, so where we can get the pressure as input and we can get the electrical output as the in terms of capacitive change. Okay. So, now here it contains two parallel plates capacitor arranged like this. It is separated by a distance d. So, one is called the fixed plate, another one is called the movable plate. So, here as you can see here, when the sound wave hits this particular parallel plate, so it keeps on moving. So, whenever there is a change in the distance between the plates, the capacitance is going to change, because this plate is connected to the electrical contact. So, as the pressure wave hits this particular capacitive plate, the electrical output is going to change. So, whenever it is changing, so it is going to change the capacitance. Why? Because we know that, so Q is equal to C into E, the basic equation of a capacitor. What is Q? The charge accumulated in the capacitor. What is E? It is the electrical input. I can say like this. So, C is equal to, so it is Q by E. Q is the charge accumulated in the capacitor and E is the electrical input. So, this is the basic equation we use for calculating the capacitance. Okay. So, as you can see in this figure, when the sound wave hits the movable diaphragm, it is called as movable diaphragm. So, the distance between the plates is going to vary, and that is where is the capacitance. Okay. So, now here the capacitance, whatever it is changing, that we have taken in a circuit, and so I have taken R. So, the load resistance. So, with the help of the capacitance and the resistance, so we can get what is the output. What is the output? So, we are trying to convert the sound wave directly in terms of electrical output. So, this is called as the pressure transducer. So, the variation across the pressure is directly proportional to variation in the capacitance. That capacitance value we have taken in the circuit, and with the help of R and C elements, we are going to amplify that, and the output whatever we are going to measure will be proportional to variation in the pressure wave. So, this is called as the pressure transducer. Here capacitor is the key element. So, that is why it is called as capacitive pressure transducer. So, as you are seeing here, there are two elements, one is capacitor, another one is R. Whenever there is R and C elements are there in a circuit, it is usually a AC variation, we get AC output. So, whenever there is R and C elements are present in a circuit, so the variation whatever we get is AC output. So, now since it is a diaphragm movement and the pressure wave, it is a sound wave. So, what will be the frequency? So, its frequency, it is from lowest frequency is 40 hertz, the lowest frequency is 40 hertz and the highest frequency is 15 kilohertz. So, with that force or with that frequency as the input, we can make this movable diaphragm to move in further, it can move in the inward and outward directions. So, this causes the changes in the capacitance, and that capacitance is taken in the circuit, and with the help of R and C we are going to get the AC output. So, this is how a capacitive transducer works. So, here we have to see two equations mainly. One is the value C. So, the amount of capacitance depend on the type of dielectric media we use and the area of cross section and the distance between the plates. Okay. And also the charges that gets accumulated in the capacitor is governed by this equation, Q is equal to CV. With these two basic equations, we can design a capacitive based pressure transducer. Okay, next is the thermal transducer. So, what is thermal transducer? So, thermal transducer are basically a transducer which converts the temperature into equivalent electrical output. The physical quantity it is going to measure is the temperature, and it is going to convert the temperature in terms of electrical output. So, that is called as a thermal transducer. So, they are special type of transducer which converts temperature into equivalent electrical output. We know that temperature we can measure either in degree centigrade or Kelvin. So, whatever the dimensions, so it will convert into electrical output. So, there are basically two types of thermal transducer. So, one is RTD. So, we call it as RTD means, so it is a type of transducer which changes its resistance whenever temperature is changing. So, that is why it is called as resistance temperature dependent. That means what? If temperature is changing, then equivalently resistance is going to change. So, we are measuring this resistance in the circuit and we are representing the change in resistance in terms of equivalent electrical output, because we know that by Ohm's law, so V is proportional to I and V is equal to IR, and I can calculate R as V by I. So, this is the basic principle of measuring the resistance. So, we are going to measure the resistance in terms of V and I quantities. Okay. So, that is what the principle of RTD is. So, next is thermocouples. So, thermocouples are again the temperature transducer which is made up of two dissimilar metals. So, it is made up of two dissimilar metals and they will have different temperature coefficients. So, two dissimilar metals are used in these thermocouples to measure the temperature. Okay. So, this is a type of active transducer. In the last class I have explained in the transducer starting topic that there are different types of transducers are available. One is called active transducer and second one is called as passive transducer. Most of the transducers are passive in nature. That means they require an external voltage for its working. Whereas this thermocouple is an example for active transducer. So, when you heat the junction of the metal or when temperature increases, so it will give the electrical output. So, that is why it is called as an active transducer. So, now thermistor is also one of the type of thermocouple only. So, here also in this thermistor, so the temperature, whenever the temperature is changing, the resistance is going to change. Okay. So, basically there are two types of thermal transducers are there. So, these two are same only. Okay. Now, so you know that, so for measuring temperature we require metals. Basically all thermal transducers are designed using metals. So, that is why we know that pure metals have positive temperature coefficient. What is positive temperature coefficient? That means, so whenever the temperature is changing, at the same time resistance is also changing. We call it as linear. It is a linear changing transducer, temperature changing transducer. So, that is why they have got positive temperature coefficient. So it is linear and it depends on the value called as temperature coefficient alpha. Okay. So next, so the thermal transducer can also be designed using some semiconductor material also. So if we design that, so it is a transducer with negative temperature coefficient. What is negative temperature coefficient? So whenever there is a change in the temperature, there is a decrease in resistance. Decrease in resistance with increase in temperature. So this is inversely proportional. That's why we call these type of transducers as the negative temperature coefficient transducers. So basically, so in thermal transducers we get positive temperature coefficient transducers and negative temperature coefficient transducers. So now let us see basically these are the three types of metals that is used for constructing the thermal transducers. So platinum, you know that it is a very good conductor of heat. So copper is also a good conductor of heat and nickel is also a good conductor of heat. So the temperature coefficient of alpha, it is for the platinum is very small. I have written 0.00391. What does that mean? It is very sensitive to temperature. With a small temperature change, it is going to give the equivalent electrical output. So then comes the copper, it is having 426, and last one comes the nickel, which is having less temperature coefficient. Now if you mix these two metals like copper and nickel, so we get the thermocouple. So there are different types of thermocouples are there. We call it as K type thermocouple, J type thermocouple. So these are some of the types of thermocouples we have. So K type, it has got two different metals used. J type also two different types of metals used. The maximum temperature from which through which we can measure using thermocouple is plus 300 degrees. We can go up to 300 degrees for measuring. Okay. So 300 degree temperature also can be measured using thermocouples. Whereas RTDs and all, it cannot measure high temperature. Maximum temperature that can be measured from an RTD is around 100 to 150 degrees centigrade. Whereas when you want to measure high temperature, we have to use either thermocouple or thermistors, because they can withstand high temperature. So this is about the thermal transducers.